Hello and welcome to lesson number 4, Rectangle System of Cartesian Coordinates. You are familiar with this and you have been for quite some time. However, I don't think you ever called it by this name. The rectangle system of Cartesian coordinates is the coordinate system where we have the two axes, the y-axis like this and the x-axis like this, and we name points by a two-dimensional number, like let's say 3, 2, something like this. This right here is the Cartesian coordinate system. We have a certain origin which is 0, 0 point. Relative to this origin, we define a different point based on how far it is in the x direction and how far it is in the y direction, where the x and y directions are perpendicular to each other. This is what we call the rectangle system of Cartesian coordinates. This system gets its name from the French mathematician, philosopher and scientist René Descartes. René Descartes, Cartesian coordinate system. So this system is actually quite useful, it's quite intuitive, and it's quite interesting in its properties. There are of course other systems. For example, there's a system called the polar coordinates, where instead of having x and y direction lengths, you instead consider an origin and tell how far away from that origin is a certain point, which is this r, and then you also tell what is the angle theta you have to turn, usually from the positive x direction, in order to get to that point. But that's not the system we use commonly. We are going to talk about the Cartesian coordinate system, a system where you have two perpendicular directions and you consider how far you have to travel along each of those two directions in order to get from the origin to a particular point. So here there are certain words we need to know. The two words we need to know are I need to spell this correctly, abscissa and ordinate. The abscissa and ordinate are the two words given to the two coordinates in this system. We don't really use these much anymore, but we usually just call them x and y. The abscissa is the x direction component. The ordinate is the y direction component. So in this particular point that I've labeled here, 3, 2, we read it from left to right, and the first number that we have is the x coordinate, which is the abscissa, and the second number we have is the y coordinate or the ordinate. So these two words are there in our syllabus, we learn them, but more commonly you will always see a person, or anyone really, saying x and y rather than abscissa and ordinate. We will always say the x-axis, we will never really say the abscissal axis or something like that. We will just say x and y plain, but these two are the words we had earlier. The abscissa for the x coordinate and the ordinate for the y coordinate. And that's really all the terminology we require. Now we are going to discuss a little extra about this coordinate system. For one thing, when you have a point, let's say this point is P. I am going to introduce you a set of notations that we use commonly to describe lengths between any points. We use the two symbols that we have assigned to those 2 points. For example, what I mean by OP, what anyone will generally mean by something like this, is the length between O and P. So here in this diagram, OP is the length from here to here, the whole entire length of the line. OP is this length. If I have another point Q, like here, Q I'll say is 5, 1, then what I mean by QP is the length from here to here, and what I mean by OQ is the length from here to here. So this is just the standard notation. This is also written in a different way sometimes, particularly in some things like, let's say, complex numbers or such. We write this as P's modulus. The modulus symbol here is generally taken to mean the size of that object. So here what I mean by this thing, which is not often used in coordinate geometry, is more often used in complex numbers. What this means is the distance of this point to the origin. In coordinate geometry we usually don't use that notation, we use this kind of notation, and in vectors of course we put extra arrow over it to indicate the direction, in which case we do tend to use this notation to say how long the vector is. But again, conventions, right, some people even write it like this, which is of course acceptable. So you need to know, whenever someone writes something like this, what they mean is the length of that line segment. So now let's discuss how we find the length of the line segment, and this is actually quite easy in this coordinate system, the rectangle system of Cartesian coordinates, because the two axes are perpendicular. And I'll show you what I mean by because the two axes are perpendicular right now. If this is the origin, this would be what we define as the 0, 0 point, because to get to the origin from the origin you need to move 0 distance in the x direction and 0 distance in the y direction. That's how it's defined. Let's say we have a point A over here, which has a location of, I'll say, x sub 0, y sub 0. These are just two numbers, it doesn't really matter what they are just two numbers. So what I mean by the A is the point x0, y0 means from the origin, starting from the origin, you need to move a distance of x0 in the x direction, which is like this, and then you need to move a distance of y0 upward in the y direction in order to get to the point A. So here we move distance x0 in the positive x direction, and we move a distance y0 in the positive y direction to get from the origin O up to the point A. So here you will notice, because the two axes are perpendicular to each other, this actually makes a right angle triangle. If I draw it out separately like this, there's some arbitrary point here, it's I'll call it B for now. We have O, we have the point A, and here we have B. So 90-degree angle at B. The length O to B is x0 and the length B to A is y0. So if you recall the Pythagorean theorem, a squared plus b squared equals c squared. So here I can write this as A is x0, so x0 squared plus b is y0 squared is equal to c squared. The hypotenuse in this case, the longest side, is OA. So therefore this is equal to OA squared. Rearranging this, I get that the distance OA is the square root of x0 squared plus y0 squared. So here we have found that the distance of a point to the origin is simply its x coordinate squared plus its y coordinate squared, whole thing square rooted. Pretty simple, pretty easy, and very nice relationship. But this is only one point relative to the origin. What if we have two different points, like in this example above? What if I want to find the distance QP? How would I do that? Well, let's explore that real quick. If we have 2 points, let's say I'll call them A and B again. If we have 2 points A, B in the xy plane relative to the origin, let's say that A is x, we'll call it x1, y1, and B is x2, y2. So in this case, if I want to find the distance O to A, I can easily find it. If I want to find the distance O to B, I can easily find it. This distance and this distance are easily findable. This distance and that distance from the origin up to the point B are easily findable. From, we'll write it on the side. OA, as we found above, is the square root of x1 squared plus y1 squared. Similarly, OB from the formula we found above is the square root of x2 squared plus y2 squared. What about the distance A to B? Well, in this diagram, what we mean by A is the point x1, y1 means that the distance from the origin that we have to travel to get to A in the x direction is x1. So I'll just mark that as x1. Similarly, the distance we have to travel in the y direction to get to A from that point is y1. So that's what this means. Similarly, to get to B, if B is the coordinate x2, y2, it means that the distance from the origin in the x direction to B is x2, and the direction in the y direction to get to B is y2. So to get to B, y2. Now consider this. If I draw this horizontal line like this, and I draw another vertical line like this, it's not really all that necessary because the two of these are right next to each other, but here you can see going from A to B vertically, I have to go an extra certain distance here. This distance is the difference of y2 and y1. You can clearly see from this level up to here is y1, from this level up to that level plus a little more is y2. So the difference of the two, the extra distance we have to travel, is y2 minus y1. So the vertical difference between B and A is y2 minus y1. Similarly, in the horizontal direction, from the origin up to this point, we have to travel a distance x1. To travel all the way to B's point, we have to travel a distance x1 plus a little extra. And this little extra is the difference of x2 and x1. So this difference here is x2 minus x1. So if we draw this as a triangle, if we draw only A and B as a triangle, if we say this is the point A and this is the point B, we could draw a triangle like this. We could draw a triangle where this side length of the base and the side length of the height are x2 minus x1 and y2 minus y1 respectively. So we have this. So now, given this, we can say, again, we have a similar situation of a right angle triangle. So we can say that the hypotenuse from Pythagorean theorem, AB squared, would be this length squared, so x2 minus x1 squared plus the other length squared, which is y2 minus y1. So we have y2 minus y1 squared. Now taking the square root of both sides, we can see that the distance AB is the square root of x2 minus x1, or the x-coordinate difference squared, plus y2 minus y1, or the y-coordinate difference squared. So generally, if we have any two points in the coordinate plane, A being x1 y1 and B being x2 y2, then the distance between those 2 points AB is the square root of the x-coordinate difference x2 minus x1 squared plus the y-coordinate difference y2 minus y1 squared. Also note that since these quantities are squared, x2 minus x1 squared and x1 minus x2 squared would be the same thing. Say x1 is 5 and x2 is 3. If we have this thing, 3 minus 5 would give us negative 2, but negative 2 squared will give us 4. Similarly, if we do it the other way and we have x1 minus x2 squared, then we would get 2, but 2 squared is still 4. So, because of that, it doesn't matter which order you consider the 2 points in, so long as you substitute the correct values, you will get the correct answer. Now that we know how to find the distance between 2 points in the coordinate plane, let's now move on to the next part that is considered in the syllabus. Within the syllabus, the next thing we are expected to do is to find a third point on a line that is a certain distance ratio away from two other points. What I mean by this is, let's say we have the point A here, we have the point B here, and we have the line joining them, AB. Extending this line outward, we can see if we put a point C in the middle, there will be a certain ratio between AC and BC lengths. What we are expected to do is find a formula for the point C based on a given ratio of AC to BC. And there are two cases in this. One case is where the point C is in between the 2 points A and B, like I've drawn here. And the other case is here, if I call this point D, the case where the point D is outside the points A and B. So here what I mean by inside and outside is, in this case, C has a x-coordinate which appears to be greater than A but less than B, and here D is either greater than A and greater than B, or less than A and less than B. It is not in between A and B. So I think it's easy to understand what we're expected to do here, but I'll point it out separately. For the case 1, we are expected to find a point C such that the distance from A to C, this distance, is m times some constant, and the other distance B to C is n times some constant, such that the ratio of AC to BC is some n to m to n ratio, where m and n are elements of the real numbers. So let's now see how we can figure out this and find the coordinates of the point C given the points A and B. So the points A and B, let us label them like this. Let's say the point A is the point x1, y1, and let us say that the point B is the point x2, y2. So then let's say that the point C that we want to find in the middle of the two is x3, y3. So now let's consider the geometry of this situation. If this length and this length have a ratio m to n, then from this construction that we are going to do here, if I construct a horizontal line from A, a horizontal line from C, a vertical line from C, and a vertical line from B, this will make a 90-degree angle, this will make a 90-degree angle, and since these two lines here, and here are parallel, and this is anyway the same line, so it's anyway parallel, we can say that this angle here, which I'll label alpha, is equal to this angle, which I'll label alpha also. Both of these angles are equal. Similarly, this angle here, which I'll label beta, and this angle here, which I'll label beta, are equal. What this means is that these two triangles are similar triangles. I will label this point D temporarily. It's not necessary, but I'll label it, and I'll label this point E. So we have this construction that we made. In this construction, we can see that D and A are both level with each other. They are both on a horizontal line, which means their y coordinates would be equal to each other. So considering the point D, D would have to have the same y coordinate as A. A has y coordinate y1, so D would have y coordinate y1. Similarly, because we found D by constructing a vertical line from C, and we didn't move anywhere horizontally, the horizontal distance from the origin to D would not have changed from point C. So C and D should have the same horizontal distance to the origin, which means that C and D's both x coordinates would be equal to x3. By a similar method, we can see that because E was constructed by constructing a horizontal to C, its y coordinate would be y3. Similarly, since E was constructed by constructing a vertical at B, we can see that the horizontal distance from the origin to E should be the same as the horizontal distance to B, which would be x2. So then D would be x3, y1, and E would be x2, y3. Now, by the fact that these two triangles are similar triangles, triangle ADC and triangle CEB are similar, if the ratio of AC to BC ratio is m to n, by the fact that these two are similar triangles, we can also say the ratio AD to CE, comparing the two corresponding sides, this side and this side, that ratio should also equal m to n. And similarly, comparing the other two correspondent sides, DC ratio to EB, this ratio and this ratio should also be the same number, m to n. So writing that, EB would also be the ratio m to n. I'm going to label this equation 1. I'm going to label this equation 2. And now we're going to use these equations 1 and 2 to help us find the point C. So from 1, if I consider 1, One says that the ratio AD to CE is the ratio M to N. If I consider AD, the length AD, A and D have the same y coordinate. So the y coordinate difference between the two is 0. But they have x coordinate difference of x3 minus x1. So then AD, the length AD is x3 minus x1. So I can write that AD equals x3 minus x1. And similarly for C and E also have the same y coordinate of y3. You can see C and D have the same coordinate y3. But they have different x coordinates. E has x2 and C has x3. So then CE length would be x2 minus x3. CE length would be x2 minus x3. From this, we can say that now we know the two lengths A to D and C to E, and we know their ratio. We can say that AD divided by CE is equal to the ratio that we have M divided by N. And then into this, if we substitute the two values of AD and CE, we can see x3 minus x1 divided by x2 minus x3 is equal to M divided by N. Doing some cross multiplication on this, we can see N times x3 minus x1 is equal to M times x2 minus x3. And now, taking this, if I distribute the N and M, I can see N times x3 minus N times x1 is equal to M times x2 minus M times x3. Taking this, if I take the x3s to one side, if I take this mx3 to this side, and I take all the other variables to the other side, I can see nx3 plus mx3 is equal to mx2 plus nx1 by algebraic rearrangement. Now, if I take the common factor of x3 out here, I get that m plus n times x3 is equal to mx2 plus nx1, which then gives me that x3, the coordinate x3 is mx2 plus nx1 divided by m plus n. So here, from this, we have found the x coordinate of the central point C that we were looking for. By a similar method, if we take 2 and we do the same thing, the two lengths that we are interested in for 2 are DC and EB. So if we consider DC and EB going up to this thing, D and C have the same x coordinate x3. D and C have the same x coordinate x3, but they have a difference in y coordinates y3 and y1. So then the DC length would be y3 minus y1. If I write that down, DC length would be y3 minus y1. Similarly, if I consider the other length I want EB, if we consider EB and have the same x coordinate x2, but they have different y coordinates. B has y2 and E has y3. So then the distance EB would be simply y2 minus y3. So I can write that down. EB is y2 minus y3. Now, using these two lengths and the ratio of m to n, we can say that DC divided by EB is equal to the ratio m divided by n. Then substituting the two values we have y3 minus y1 divided by y2 minus y3 is equal to m divided by n. Rearranging, we get, I'll just do it in one quick step here, ny3 minus ny1 is equal to my2 minus my3. Taking the y3s to one side and taking the other values to the other side, we get n plus m y3 is equal to my2 plus n y1, and then finally we get y3 is equal to my2 plus ny1 divided by m plus n. So these two have the same exact format. The coordinate x3 and the coordinate y3 have a similar format as we can see. If we write this in summary, the coordinates of the point C are mx2 plus nx1 divided by m plus n, comma my2 plus ny1 divided by m plus n. We can see something interesting here. What we have derived appears to be a weighted average of the 2 points A and B. It's a weighted average. We are weighting the x2 point by a weight m, and we are weighting the x1 point by a weight n, which is kind of intuitive. If m and n are both equal, i.e. we want the point that has a ratio of 1 to 1 between AC and BC, i.e. we want the point that is the midpoint of AC and AB. If we want the midpoint of AB, we want the point that has a ratio AC is 1 to AB 1, which intuitively would be the average of the 2 points A and B. And we can clearly see that holds, and it holds for other values also. So you can try substituting different numbers into this and see what happens. But this is the formula for a point in between A and B that has a ratio AC to BC of m to n. But I told you there's another case, and in fact there is. There is the case where we have a point C. If we take this as A, if we take this as B, there is the case that we have a point C which is outside of AB but has a ratio of AC to BC equal m to n. So what this looks like, what this means is that this length is AC, this length is BC, where C is outside of the line AB. You can clearly see C is not anywhere in here, C is instead outside of this line, and the ratio here is still m to n. So in this situation we have the same exact argument, but we have a different thing. We have subtraction is different because C is outside of AB line. If I label A as x1 y1 again, and we label B as x2 y2 again, and we label C as x3 y3 again, this time I'm going to skip this construction. I'm going to draw it, but I'm not going to mark the points or any of that. We are simply going to apply our knowledge as is. We are simply going to apply our knowledge as is to find this answer. So here, considering the distance A to C, the x-coordinate difference between these two is x3 minus x1, and the y-coordinate difference between these two is y3 minus y1. So therefore, AC's horizontal distance, which I am going to label as AC with a horizontal arrow above it, is going to be x3 minus x1. Because horizontally, if we find the point that's over here, these two would have the same y-coordinate, just that they have different x-coordinates. Similarly, the horizontal distance is x3 minus x1. The vertical distance AC, which I'm going to denote it like this, is going to be y3 minus y1. In the same way, if I take the horizontal and vertical distances of BC, if I write them in the same way, horizontal distance BC and vertical distance BC, I will find the horizontal distance from B to C. This distance I want to find is, horizontal distance from B to C is x3 minus x2. So BC is x3 minus x2. Similarly, the vertical distance from B to C is y3 minus y2. The difference between these two cases is, in fact, this second one. Because earlier C was between A and B, I wrote this in the other way. I wrote x2 minus x3. In this case, because x3 is outside of AB line, x3 is greater than x2, meaning that in this case, BC, if I wrote BC as x2 minus x3, it would be the wrong side around. It needs to be x3 minus x2. Similarly, vertically, it is y3 minus y2, not what we wrote earlier, as y2 minus y3. So now again, if we do the same thing, considering these lengths and considering the ratio of AC to BC should be m to n. So AC horizontal divided by BC horizontal by the similar triangle argument should also be equal to the ratio m to n. Also, by the similar triangle argument, AC vertical distance to BC vertical distance should also be equal to that same ratio m to n. Let's now solve these simultaneously. On the left side we will do the horizontal distance to get the x coordinate. On the right side we will do the vertical distance to get the y coordinate. On the left we have x3 minus x1 divided by x3 minus x2 is equal to m divided by n. Cross multiplying we get that n times x3 minus x1 is equal to m times x3 minus x2, which if we expand gets us nx3 minus nx1 is equal to mx3 minus mx2. Now taking this, if I take all the x3 terms to one side, I get nx3 minus mx3 is equal to nx1 minus mx2. Now taking the common factor of x3 out of the left side, we can see x3 times n minus m is equal to nx1 minus mx2. Finally, we can see that x3 coordinate is equal to nx1 minus mx2 divided by n minus m. If we do the same exact thing on the right side, we have y3 minus y1 divided by y3 minus y2 is equal to m divided by n. If I cross multiply, I get n times, I will actually skip this a little bit, we get n times y3 minus n times y1 is equal to m times y3 minus m times y2. Taking all the n's and m's to one side, we get that y3 times n minus m is equal to ny1 minus my2, which then gives us that y3 is equal to ny1 minus my2 divided by n minus m. We can see again this is not exactly the same format that we found earlier, it's a slightly different format. Instead of a weighted average, we kind of have weighted difference average. It's a little strange, but we have a similar form to what we found earlier. It's just that instead of pluses here, we have minuses. Instead of pluses here, we have minuses. Note that also by symmetry of the minus sign, if we multiply the top and bottom by minus 1, we can also write this in the other form, saying that x3 is equal to mx2 minus nx1 divided by m minus n, and also y3 is equal to my2 minus ny1 divided by m minus n. These are exactly the same thing, there's nothing wrong here. So choose which one you like and apply that one. This is the more commonly written one, so that's why I wrote like this. And this is if m and n are not equal, because in this case if m and n are equal, the denominator here would go to 0, which means we're essentially dividing by 0, which should not happen. And I'll tell you why this seems to happen and why we seem to be dividing by 0, and when you divide by 0 or you divide by a number close to 0, you appear to be going to infinity. The reason is, if we consider a line like this, A, B and an external point C. Let's say AB and BC are equal, which means this has a ratio 1 to 1, which means that AC is 2, and therefore the ratio AC to BC is 2 to 1. If I make C double the distance away, if I draw this line, continue it, instead mark C here, now this length BC is a distance of 2 and the length AC is a distance of 3. So ratio AC to BC is now 2 to 3. If I push C further and further away, if I push C even further away, let's say I push C such that BC is 9 away and AC is now 10 away. Let's say I bring B really close to A. Now this is 1, this is 9, and the total length is 10. So now the ratio of AC to BC is 10 to 9. Notice that 10 to 9 is very close to 1. If I push C even further away, if I push C very far away and I take B extremely close to A like this, such that this distance is 1, this distance is 99, and this distance is 100, notice that now AC to BC length is now very close to 1 to 1. The ratio 99 to 100 is very close to 1 to 1. But of course it will never reach it. We can push C arbitrarily far away and we will get a ratio A to A plus some delta, where delta is very small but not 0. Delta is not 0 but delta is very small compared to A. But because of this, A plus delta divided by A will never equal 1. In the limit it will, as you make C infinitely far away, because then the distance AB will become insignificant. But this is the reason why it appears that we have a divide by 0 when we want M and N, the ratios of the two, to be equal. It's because it simply doesn't happen. There's also another issue. It's the issue that there is another point on the opposite side that does the same thing. If we consider this point, which I'll call C dash, on the other side, this could also be 99, in which case we are getting the same thing. Another point on the opposite side of AB, which is also having a ratio very close to 1 to 1. So the issue here, the reason that a divide by 0 occurs, is because the point that is equidistant from A and B but outside AB would be at an infinity. So generally in this formula, we do not have M equal to N, we say M not equal to N, or we say for M not equal to N. But just now the reason that M equal to N appears to give us a divide by 0 error is because the point that we are trying to find is going to be infinitely far away from A and B. And that concludes the lesson for today. I was actually surprised that this was all that was there within the syllabus. There's a lot more to talk about in Cartesian geometry, but they will be covered in future lessons, not in this lesson as per the syllabus. So, in summary, what we talked about today, we discussed the Cartesian coordinate system and how we already knew it, but we didn't know the name of it. It is simply the xy plane where points are described by a pair of numbers, one number which we call the abscissa or the x-coordinate, and another number which we call the ordinate or the y-coordinate. We write them in the form of of brackets with a comma in between the two numbers. We call them the x and y coordinates, and we learnt, given a certain point given by x and y, we learnt how to find the distance from that point to the origin. If we call this thing x0, y0, then this point A is a distance of x0 squared plus y0 squared square root from the origin. We learnt how we denote these lengths as the 2 points names right next to each other. In this case, the length of A from the origin O would be denoted as OA. Then we learned, given 2 points, how to find the distance between the 2 points. If we have A is x1, y1 and B is x2, y2, then the distance AB would be the square root of the difference of the x coordinates x1 minus x2 squared plus the difference of the y coordinates y1 minus y2 squared. And we noted that it doesn't matter which order you subtract the 2 in, because we are squaring it anyway, so the difference will anyway give us a positive number. Furthermore, expanding on this idea of the line's length, the distance between 2 points, we found the formulae for a point C that is on the line AB and either in the middle of A and B or external to A and B. And we found how to find that point's coordinates given a certain ratio AC to BC, which we labeled M to N. In the in-between case, we found that the coordinate C is M times x2 plus N times x1 divide by m plus n, comma, the same exact thing for the y coordinate, m times y2 plus n times y1 divide by m plus n, where x2, x1, y2, y1 are the coordinates of the points A and B. Similarly, in the external case, we found that the point C is given by m times x2 minus n times y1 x1 divide by n minus m minus n, where m and n are not equal. We then discuss the problem with m and n being equal, and we discuss what's actually happening as m approaches n. When m and n get really close, what's actually happening is that the point we're trying to find is going to infinity. And that was the end of the lesson. Thank you for watching. Subscribe to the channel, and goodbye.